Hi, and welcome to Digital Tech Lunch at FINN. We're very pleased and happy to see so many of you here today. Today, Haimanot, Tekie, and Greig, two of our talented developers, will introduce the core concepts of event streaming and how one might use open source technology, ksqlDB, I might not use the correct pronouncement, I hope so, to effortlessly create real-time event streaming apps. We will start off with some presentation, of course, of Dave and Haimanot, but also finish off with some Slido as always. So please share your thoughts, comments at #TechLunch. But now, take it away, Haimanot and Dave.
Hi, everybody. Wouldn't it be super cool if building stream processing applications could be as easy as building CRUD applications? Well, that wish is not something that is that far-fetched anymore because ksqlDB, an event-based event streaming-based database, is purpose-built to make creating such applications simple. We came across this technology in one of our knowledge days, and today we want to share our findings with you. My name is Haimanot, and I am a full stack web developer at FINN.
My name's Dave. I'm also a full stack developer at FINN.
So our agenda for today looks something like this. Since ksqlDB is built with Apache Kafka in mind, or working with those easy in mind, we thought we would lay the foundations or have a quick overview of what Apache Kafka is. This might not be that big of a news to some of you that have used this, but yeah, we're just going to talk a little bit about that. And then after that, we will talk about what makes building stream processing applications difficult. And we'll talk about how ksqlDB eliminates those complexities. We will have a little demo, and we'll talk about some of the limitations that we came across. And as Frida mentioned, if you have any questions, comments or thoughts, just put them in Slido, and we'll try to answer as best as we can. We don't have ksqlDB in production right now, but it's definitely something we will keep an eye on going forward. So Apache Kafka, it's a stream processing, or it's a stream or an event store. It's an open source. In the Kafka world, an event is a representation of something that has happened at some point. And those events are stored in a topic. So a topic is a log file persisted in a disk. Those events can stay there for as long as we want them to. But since the topic is a log file, persisting it in one disk will limit the size of the topic to that disk size. So Kafka has introduced this notion of like partitions, so that a topic can spread across several partitioned logs. And this will enable Kafka to be easily scalable. And those topics reside in brokers, and the brokers are just nodes connected over network, and a collection of those brokers make up a Kafka cluster. So that's Kafka. And then to be able to interact with it, we would use producers and consumers. A producer, those are like clients that where a producer is an application that would write events into, or source events into Kafka cluster. And consumer is a client that would read those from the cluster. So a little bit about what makes building event streaming applications a bit difficult. For this talk, we will use a simplistic example. Let's say we have an ad management system where users can use this system to add an ad or update some information about the ad. And we're building this event-driven application. So whenever a user creates an ad or updates something about the ad, an event will be created. So how do we get this event into Kafka? To do that, we will we can do it by creating a producer application, and it means we'll have to write, language like Kotlin or Java or something of the like, and we would source those events into Kafka using the producer API that Kafka offers. And also we need to serialize our event key value. And we will have another way to source those events into Kafka would be using Kafka Connect. And for that, we might need we would use Kafka Connect to source events from, for example, databases. So the changelog in a database would be sourced as an event into Kafka. But then that means we'll have to stand a cluster for Kafka Connect. So already here we've got two moving pieces. Now that we have our events stored in Kafka, we want to do something with them. Maybe we want to answer the questions about our ads. Maybe we want to know what is the latest version of this particular ad, or how many ads change over the last X amount of time. How many views does an ad have right now? Or how many views happened as a result of something changing in an ad? To get an answer for such questions, we would need to process our stream of events. For this, we will need another moving component, stream processing component. It could be Kafka Stream or ksql. Once we have worked with our stream and transformed it into a desired shape or format, then we can go ahead and load it into either a traditional database for applications that need a synchronous way of accessing data, or for that we could use Kafka Connect to load those transformed streams data into a traditional database, or we could just source it into another stream so that other applications can use it. So already here we see that there are several moving components, but with ksqlDB, all those moving components gets contained within this ksqlDB. We can connect with external event sources using a couple of SQL statements, and we don't have to leave ksqlDB for that. So we're just standing up like ksqlDB cluster or a server, and that gets to using simple SQL statements. It can source events from those external applications or resources. And we can, within ksqlDB, using, again, simple SQL statements, process our stream and get the information that we need. We can view the results either as a table or as a materialized view, still within ksqlDB. So the only dependency that this approach of building stream processing applitions, the only dependency that we have is to Kafka, actually. And then applications could just use the interface that ksqlDB provides to get whatever data they need from this ksqlDB. So what we get is like from having many moving components to achieve building stream processing applications, we get it down to just one thing that we need to be concerned with. And now Dave will walk us through the core concepts in ksqlDB. Take it away, Dave.
Okay, awesome. So now we're going to break up some of the core concepts of ksqlDB and have a look at the technology that underpins it. So we'll start with stream processing. So firstly, in ksqlDB, we have this notion of a stream, and a stream is a ksqlDB object type. It's essentially an unbounded series of events, so it's very much like a Kafka topic. Data inside a stream is immutable, so you cannot update it, you cannot delete a record, but you can, of course, when something changes, instead of changing the existing entry like you would in a database, you would just trigger a new event and then append that to the stream. So when you create a stream in ksqlDB, you can use either an existing Kafka topic as your data source, or you can create a new topic altogether that producers can then publish events to. So one important notion, though, that differentiates a stream from a Kafka topic is that you must have a schema. This is because it's very hard to reason about the data inside your stream like you would normally with SQL, unless you have like a very rigid schema. So the flexibility of ksqlDB means that you can create a stream from a topic using just a subset of the event data that you care about. So if we look at this example here, we have a single Kafka topic. Here it's got 3 producers on the left-hand side. They could be different systems that are producing events that persist data to the topic. This topic here is a collection of ads, I guess we could say. So the idea in Kafka with a topic is that you would have you would co-locate similar events that have similar concerns. So here we have in the red event we have an iPhone 10 for sale, and in the blue event we have a holiday cabin on a mountain for rent. And you can see that they're similar but they're different. So while they have some things like an ad ID or a status, that's pretty consistent. Some things aren't, like a brand. We have a brand for electronics and goods like that, but it makes no sense having a brand for a cabin. And the price is also different. Maybe with a cabin, instead of having a static price, we might want to have a variable price range because the rental market dictates different prices depending on demand. So while these belong in the same topic together, it can make it difficult to reason about the data. So if we were to create a stream from this in ksqlDB and we only cared about a few things, we can do that easily. So we would create it based off this topic. And you can see in the middle there, the syntax create stream adds, and then it has some column names and some types. It's very much like SQL. And then you can see in the resulting stream, we have our events, and they've just been filtered. So we don't have those things like the brand or the price range. We've just got the values that we cared about. Of course, you can also create a stream using all the keys from events in your topic, but you'd need to explicitly declare them. One cool thing though is that ksqlDB is very much aware of schema registries. So if your Kafka topic uses something like Avro, ksqlDB can understand that and can read the schema from the schema registry, and you can just use that as shorthand to create your stream without having to explicitly declare everything. So the next concept worth mentioning is connectors. As Haimanot mentioned earlier before, Kafka's only as interesting as the data that goes into it. And in a traditional application, you would use something like Kafka Connect to connect something to a Kafka topic. So in ksqlDB, we're using Kafka Connect under the covers so that you don't need to. And Kafka Connect is a tool that just enables the import and export of data sets into a Kafka topic. But that's all it really does. It doesn't do any stream processing. It's deliberately designed to only manage concerns about where the data in your Kafka topic came from or where it should go. So normally that would mean developers would need to set up connections with Kafka Connect, but in ksqlDB, it's simply a SQL statement, and the complexity is abstracted away. There are two types of connectors that you can create. There is a source connector and there is a sink connector. So source connector, as the name implies, allows you to import data into ksqlDB as a Kafka topic. So this is helpful if you want to import data from another source and reason about it like you would in a normal relational database. Perhaps a more interesting use case would be that you would take this source data and then enrich it with the data from existing Kafka topics, joining it to create a new stream altogether. So then the opposite of a source connector is a sink connector that allows you to push data out of Kafka and ksqlDB into an external system. So it will take a topic, and usually with the assistance of a plugin, it'll publish the contents of the topic to whatever system you like, be it Elasticsearch or PagerDuty or another database. And at last check, there was 195 plugins available for Kafka Connect on the Confluent Hub. So it's super easy to integrate Kafka with your preferred data source, and you don't have to worry about a thing. So now moving on to materialized views. So materialized view is database terminology for the result of a query. It's basically a read optimized or cached view of some data. So in ksqlDB, you can have streams and you can have tables. And in the context of materialized views, we're talking now about a ksqlDB table, and one that uses some sort of aggregation on the data in your topic or stream. So a materialized view essentially works by running a query against the delta in the stream of data. And that's how ksqlDB can achieve real-time aggregation with fairly efficiently, because it's only doing it on the changes every time a new event gets added to a stream. So a table in ksqlDB is pretty much the same as a table in a relational database. I mean, by that, they can contain a primary key. You can join them with other tables. You can actually also join them with other streams. And a table can be created either off the back of a stream or a Kafka topic directly. And tables are useful for containing a view of data from Kafka or your stream in its current state. So we leave all the historical stuff to streams to deal with. Tables just give you a view of what is true now. So that means that the data inside the table is mutable and events update with the latest record. Tombstone events are deleted from the table. So a tombstone event is a Kafka concept where a record has a key but has a null value. And this concept is around because Kafka topics essentially, it's a list of append-only list of events. So a tombstone is logically a record of deletion. But obviously your data is never really deleted. It exists as a changelog of events in a Kafka topic. But here, so that we know not to care about it anymore, if we see a tombstone event, it will be removed from the table. So a table and a stream is actually very similar. In fact, they're sort of two sides of the same coin. And in the Confluent documentation, they often refer to this table or stream table duality. So you can have a stream as a table. A stream can be considered a changelog of a table, as the aggregation of a stream of updates over time yields a table, or a table is a stream. A table can be considered a snapshot, a point in time of the latest value for each key in a stream. The observations of changes to a table over time is what yields a stream. And you can sort of see the differences here as well, just to summarize. So when we have a new event coming in and that key hasn't been read before in a stream, it's inserted. In a table, it's also inserted. When we have another event using that exact same key coming through in a stream, it's just inserted. But in a table, we update that record or that row. And then when we get the tombstone event, so the key comes in, but it has a null value, then we delete it from the table. And in the event that a key comes in that is null, well, the stream still accepts it, but the table completely ignores it. And the last part of the materialized views section, I guess, that's worth mentioning is queries. So it should be kind of obvious by now that ksql is leveraging a SQL-like language. And that's because SQL is commonly used and widely understood. So ksqlDB is trying as hard as it can to avoid introducing yet another bespoke query language. So while there might be some little differences, for the most part, queries are written like regular SQL. And there are three types of queries you can write. There's a persistent query, and that's one that just runs forever. And that's used when we create a stream or a table from a query. And we'll sort of see an example of that one a little bit later. There's also a push query, and a push query is one where a client subscribes to a result. So the way I remember this is I think of like getting push requests every time there's an update. But basically, it's a kind of query that will just keep running until the client tells it to stop. In the ksqlDB CLI, there's the telltale sign that you are writing a push query is that you've probably written at the end of the query emit changes, which just means just keep pushing out all the changes until someone counters the query. The result of a push query is not persisted anywhere, unless, of course, you use that push query to create a stream or a table, and then it becomes a persistent query. And a pull query is basically a query that just gets you the current data as of now. So it's analogous to the queries one would normally write when querying a relational database. So they just fetch the state of a materialized view, and the result of a pull query is not persisted anywhere. Okay, so what kinds of things can I do with ksqlDB? Well, you can do a lot. So we started looking at it as a way, as a tool to sort of reason about the data that we had inside some of our Kafka topics at FINN. And we started playing around with it, mainly through the CLI tool. But you can build entire applications with it. So you can explore all the data in various topics, or you can aggregate that data in real time. And you can also just query the data based on time windows in real time, which is super cool. And you can also join data effortlessly between streams and tables, and you can sort of enrich the data that you have and then get that data back out. So we're going to now try and go through a bit of a demo. In order for this demo to work, we have taken the starter kit from the ksqlDB site, and we're running it all on my laptop. So part of this will set up a topic broker, Kafka broker, sorry, Zookeeper as well to manage the broker, the ksqlDB server, and the CLI as well. So that might sound like a lot, but it's literally one Docker command. And I'm just making this point now because it can be quite intensive for one computer to run. So fingers crossed we have no issues, but I will just bring up that demo now. Okay. So now we have ksqlDB. This is the CLI tool. And we're going to start off first. Let's actually just check that there's nothing up our sleeves. Cool, it's empty. So basically we just have the out-of-the-box processing log that comes with ksql. So now I'm going to create a stream. So in order for me to create a stream, it's literally this syntax here. So I've created a stream. I'm calling it ads. I'm explaining what I want in it. I want an ad ID that's going to be a big int, status, ad type. Both of those are a varchar, a price, and a timestamp. And then this next part is the interesting part. So we didn't have any topics, we didn't have any streams. We basically are just running this all out of Docker right now. So this topic here, ads, didn't exist before. Now it does because I created the stream. And this value format of JSON is just, I guess I could have chosen Avro or another schema type, I guess. And the partitions is how many partitions for the topic. So I can actually show you now that that's created my ads topic. Let's create another stream because one stream's not super interesting. So let's create another stream where maybe instead of just keeping the ads, maybe we also want to know how many times users have viewed an ad, because that could be interesting data. Okay, so let's just create the views stream. Okay, so like before, I defined the name here. I define the contents of the stream, and then here I have a new topic, add views. So we can see it's created. Cool. So I'm going to do one more thing before I start populating with data. I'm basically going to tell ksqlDB that when I read from these topics, at any point in time, just always give me the start of the topic onwards, because I want all the historical data. Sometimes in production, you wouldn't do this because maybe you only care about data from now onwards when you start your application. But in this case here, we don't have a lot of data that we're populating it with. So that's what that command does. It just basically just flips a switch in the settings and says to start from the start of the of all the topics. So if I wanted to insert some data into one of these streams, I could do it. I could do it explicitly in ksqlDB like this. It would literally, it's just the same as a normal insert statement in SQL. However, you probably wouldn't normally do it like this. Instead, your data is probably going to be coming either from an existing Kafka topic, in which case you'll have a producer just producing to your topic, and we would have created the stream off of that topic. Or you could take the data from a connector of some sort, which again creates another topic. Or we can do something, we can cheat a little bit, and we can use the REST API that comes out of the box with ksqlDB. So over here, I have a little script. If I run this here, this will basically run an insert statement. It has some random data, and it's just inserting a new ad every 3 seconds. And if I go back over here, I can show you what my stream looks like. So I'll add my emit changes because I want to see it in real time. And now we can see the data updating as it comes in. Another cool thing I can do actually is I can aggregate this this data in real time. So maybe I could maybe instead of aggregating the data in real time, well, actually we'll do that. We'll add in some extra data from the view. So if I cancel this query, if I just maybe I wanted to see how many ads, how many times an ad is repeated in that stream. So this random data, every time an ad is updated, we're inserting a new record. This is going to show me the second column here, which I have not named. So ksql is just giving me the default. It's basically just giving me the aggregate here in real time. So because we're reading the stream as it's being populated, it's possible that you may see a record here that gets repeated later on here, but the values change. And that's because it's in real time just calculating and adding it. That's great for streams, but if you wanted to know what is the current number of changes or what is the latest status for that ad right now, that's when you need to have a table and have a materialized view. So let's do that. Let's have a table that gives us the latest price and the latest status for any ad in our stream. So this is our syntax. We're basically calling it current ads. That's the name of the table. And we're just saying create it based off of this query. And this query is saying, give me the ad ID, and then give me the latest by offset, which is an aggregate function in ksqlDB. So this is not a normal SQL function here, but it's basically saying, just give me the latest price for any record that matches this ad ID, and we'll call it latest price. And let's do the same for the latest status. And we'll take it from the ad stream, and then we're going to group it by the ad ID. And now I can query this directly. Okay, and then I'm not too sure if this record is going to update again, because as I said, it is random data. So if I run it again, I don't see any changes to the status or the price, but that's okay. It's probably eventually going to happen at some point, but because this is random data, it's probably not very predictable. The other cool thing though is, instead of just querying directly through the command line like this, I could also query via the REST API. So I have that over here. Basically, I've just basically said this is my SQL statement, and I've just posted it to this query endpoint. And then with the response that's come back, I've just asked it to pipe it out to JQ just to pretty print it. But you can see, here's the columns, and here's the data for the columns in each row that comes back. So that's pretty cool. It's just another way to get the data out. Okay, so let's see. We have some ads now. Maybe we should also add some views. So the ad views, this is going to be, I guess, every time a user looks at an ad, we have a record, and you can see it's just populating much more faster. We're putting an ad in a view record in every second. Okay, so now we can try joining these two streams together to see what is the intersection of like ads and views. So let's try this. Okay, so we have our select statement saying, give me the ad ID here and count the number of views for that ad ID. And we're doing this in a join here with a time frame, because we're joining two streams together. Joining two streams together means that there is a temporal concern we need to have. A stream could have events that come in at different times. So we need to sort of have some sort of tolerance. And here we've given it quite a wide one. We've said within 1 hour, but that's just so you could see some data updating. So now we're getting a real-time aggregation of how many people have viewed what ad. So that's super cool. Okay, so there's a few other things that we can do in terms of talking about timeframes. And one of the things that ksql does really well is this notion of windowing. So maybe we're interested in how often an ad has been updated over the course of a 1 minute window. Maybe there's a use case that says if someone's updated an ad more than 3 times within a 1 minute tolerance, then maybe our UX isn't great and we need to look at why they're having to change their ad so much, or are they having trouble trying to price the item that they're listing? So we can do that by creating a table. We'll call it multiple edits. Okay, and that's going to take data from the ads stream, and then this window tumbling command is basically just looking at 1 minute intervals and grouping all the ads within that 1 minute interval where the total count is greater than 3. So now see if we can see this update. Well, great, we have some data coming through, so we can see at least 2 ads have been updated 4 times in total over that 1 minute window. And if we leave this running long enough, we may see more. It could also be that because we're inserting an ad every 3 seconds, it's not happening or the data isn't as interesting to us. There's not as many occurrences of this. Maybe in that case, a more exciting use case would be the number of times the user has viewed an ad in a 3-minute window. Now I can create a table, or I could also just do, I should just be able to do it as a select statement here. So here I've said, give me the user ID, the ad ID, and the number of how many times they've viewed that ad, we'll call that a view tally, from the views stream in a 5-minute block. And only give me the ones where they've looked at it more than 3 times. So we can see user 1 was interested in this ad because they looked at it 4 times within a 5-minute window. Maybe that user is responding to changes in the ads, or maybe they're just really hoping to buy that item. And then I guess one more interesting thing you can do is you can do windowing and joining at the same time. So maybe we want to look at the types of ads where a user is viewed more than 3 times in a 5-minute window. So remember, we had like an ad type ID. So sort of like a real estate ad or electronics ad or what have you. So here we are basically, this might be asking a little bit too much of my computer at this point in time, but here we are asking for all the information where a user has viewed something, which ad type it is, and aggregating on that ad type within 5 minutes, and where the count is greater than 3. And I'll just in the background, these scripts are still running and they're producing a lot of data, which is also chewing up a bit of memory. So we may, in fact, be asking too much. Yeah, I think we are. That's okay. I do have something prepared where I can show this last example directly, and then that was actually, thankfully, the last part of the demo. Okay. So if I just quickly bring up that last example. And share that for you now. Okay. So here you can see in a case where my computer had a little bit more memory and was able to satisfy the constraints, we were able to get the information out from the user's stream or the view stream and join on the ad stream and tally it based on the number of views exceeding 3. And you can see that some users have viewed a lot of the same types of ads. And this is doing the same thing, but as a materialized view. So we're creating it as a table, and then we can query that table directly by just using a select statement. And this will say, just tell me this one user ID and this one type of ad and how many times. And you can see that they have viewed it first 279 times, then 285 times, then 301 times, because the data is constantly updating in real time. Okay, so I guess that concludes the demo, but I did want to mention some of the limitations around ksql, or some of the gotchas that we encountered at least. So in order to join in ksql, you must have partition count must be balanced on both sources. So if you have 2 topics in production and one topic has 20 partitions and another topic has 5 partitions, you won't be able to simply join those because it's not balanced, and ksql needs things to sort of be evened out. So you would have to do what's called repartitioning. which is not difficult. It's just an additional step you need to consider. So you would have to create another stream, and then you would have to, when you create that stream, you would have to specify how many partitions you want to create. And you would have to either bring one of your streams up to 20 or down to 5, what have you. But as long as they're balanced, then you can join. And when you're joining with tables, it can only be done on a tables key at the moment. So a foreign key join is not yet supported. There is an open issue on GitHub, so that is likely to change in the future. ksqlDB is awesome for real-time aggregations and everything else, but it's sometimes you just want to look at the most recent data in a Kafka topic, and maybe it's not that straightforward because you would need to do something like the select latest offset for each key in your event, and that can be cumbersome just to do that simple lookup. You can't query an entire stream really for just that one event, because that would be super inefficient. It's really not designed for that. That's why you have to create that materialized view to cache the data. The technology is relatively young. We still are not in a major version. We're at version 0.0.17. But having said that, already this year there have been 3 releases. So it is quite an active community that's working on the technology at the moment. And it is open source, so feel free to contribute. And as you saw, it is potentially resource intensive. However, I should state again that it's unlikely that you would run your Kafka brokers, Zookeeper, ksql server on top of the one machine. Like that is sort of asking a lot. But it is possible, but yeah, it can require a lot. If you're interested, you can find out more info at ksqlDB.io, and Confluent also have some excellent tutorials on the topic that you can play with. Cool. So I guess that concludes our talk, but I'll open it up to if there are any questions on Slido.
Okay, I think I'm gonna maybe pull up Slido and read through some of the questions. And thank you guys for the questions. So Stig is asking, how is error handling implemented in ksqlDB? That is, if an event has some unparsable data, what will happen with that event?
Oh, yeah.
Yeah,
no, that's a good question. We didn't explore that too thoroughly when we played with it, but we did notice when we first attempted to play with ksqlDB that we were getting a lot of errors in the ksqlDB logs, but no results on the screen. So I guess it's a matter of configuration. The logs can be noisy, and you can ask it to filter out, or by default, I think it just filters out any failures. So your queries, your stream should just sort of fail silently. Or you can be much more explicit and ask it to throw.
But it's, I mean, underneath ksqlDB is like there's a producer and consumer, right? So that's if we're trying to source events into a topic and it doesn't meet the schema, the structure that is described in the schema, then it would just not, it will reject that that query to insert that event, but it will keep going, and then, like Dave said, it will log that error, and then I guess it would have to go to the error and figure out what is failing, I suppose. Okay, can you see the Slido, Dave? Should I go and read the next question, maybe?
Yeah, that'd be great.
Henrik is asking, how would you deploy this? I guess it would need a persistent disk for storing the materialized view, or can you use PostgreSQL for that?
Oh, that's a good question. So I guess the I guess it all happens within the ksql DB server. We haven't tried to deploy this, so I am a little bit fuzzy on some of the I guess some of the details. But as far as I understand it, every time the server is running, or if you have a cluster of servers running, then it sort of just, I think it's sort of like the data is ephemeral. It's made. I don't think it's persisted. I think it's just, this stays within the disk of the running instance. Could you export it? Yes, you could definitely do that if you had maybe some need to keep it more readily available, or just keep it. Maybe you want to actually export it anyway, so that you can sort of visualize it better outside of ksql, or see it in Splunk or Elasticsearch or something like that.
Yeah, it's just a matter of using the connect within ksqlDB, isn't it? Because you just write some SQL statements to point the result of whatever you're transforming into the desired place to output.
Yeah.
Those events, or those transformed events. Okay, there's one more question. How well do the aggregate functions scale?
So I guess some of the aggregate functions are going to be quite intensive, especially if you have a lot of them or a lot of data. And you can sort of scale, so you can scale your instances vertically or horizontally. So you can add more CPU and more memory to the instance, and hope that that's going to solve your problem. But you could also scale horizontally and have more ksqlDB servers running in, I guess, a cluster to share the load. And that should sort of, there is actually quite a good section on performance tuning ksqlDB for production. But that's something you would definitely have to consider when it comes to very intensive queries or multiple aggregations.
From what I can remember from the top of my head, it said like it seemed like the consumers, how you would, if you want to add more consumers to the same consumer group, then that's how you would scale if you want to consume more like faster, right? Consume events faster. So I remember they said something about like adding the ksqlDB with the same server ID, and there was one more configuration value that you have to give it to indicate that this is a ksqlDB of the same instance. So if you want to scale horizontally, you could do it that way.
You could also, I guess, ease the burden by making your aggregates produce something to a stream that's going to go to a Kafka topic that would then sort of exist on your broker as well, and then that could probably assist in some way as well.
Right. Stig is having a follow-up question to that error handling, and say, ref error handling. Have you seen a way to send problematic events automatically to a dead letter queue or something?
I haven't, but that's probably a really good idea, so that you have like a safety net in the event that a record can't be processed. I mean, if your record can't be processed and it's coming from a Kafka topic, and your stream is built on top of the Kafka topic, for example. So if your record isn't being processed because the data is bad, you can sort of alleviate that concern by using schema registries, I guess, to sort of make sure that the data that whatever your producers are putting into these topics is sort of consistent. But how do you handle when a particular error fails and find a way to reprocess it later. I couldn't say. I don't know if you know Haimanot.
Yeah. No, we haven't tried. We haven't gone to that route yet. But it seemed to me like it's like you would be dealing with whatever ksqlDB has put out into the logs, right? So it would be more like, how do you react to those things in the log? But it's true, we haven't really had a closer look at that. So
yeah,
sorry
I
about
can
that.
say that there are like a lot of environment variables that you can set when setting up the server, and a lot of them are around failures and what have you, but haven't really researched or looked into it very deeply. So yeah,
Right.
definitely a good question though, if you are going to take this into a production environment.
Yeah, there are some extra things to figure out first, I guess. Oh, there is one more follow-up question from Henrik. I guess we'll take that first. And I guess deploying this in Kubernetes for a high volume topic would be difficult. Every time a pod restarts, I would have to reread the whole topic log. So this is a follow-up question with that. What was the first one? Could you write it? Could it persist it? The first question Henrik asked about if you can write whatever you've processed in ksqlDB to Postgres or something, or to disks. So this is a follow-up question that's saying deploying this into Kubernetes for a high volume topic would be difficult, because every time a pod restarts, I would have to reread the whole topic log. I don't think you have to, because if you persist this into, because if you want to process your stream and transform it into a shape and form that you want it, or like if you have this materialized view of that contains the data that you're interested in, you could write that into like PostgreSQL, right? So your data will be there, if I'm getting the question right. So you would not need to have to, if a pod restarts, you would not need to reread the whole topic to get the same result again. Do you have something to add, Dave?
Yeah, I'm not really certain, but I would imagine that there is some sort of mechanism for at least like keeping place, or it is. I guess it does depend on your queries as well. Yeah, no, I don't really have a clear answer for that. Sorry, I guess I'd have to sort of go back to the docs and research that particular case. Yeah.
Right. There is one more question about is ksqlDB production ready?
Yeah. I mean, it is. You can definitely use it in production, despite the fact that it hasn't hit a major version. I guess it comes down to your particular appetite for using sort of early technology. But the other thing that is actually kind of cool with ksqlDB is that you can lock down the CLI, so you can protect your production environment to make sure that the CLI isn't available and that your application instead just starts up and reads a SQL file and will only accept queries from that file. So that's kind of nice. It just means that anybody that's relying on the data knows that it's only being handled by that one source. And the other thing you can do is you can, or I mentioned the scaling, but you can also update queries on the fly. So you can do like a create or update statement for any of the streams or tables you have. So that kind of makes it a lot easier to sort of have like a zero downtime if that's a concern.
Right. The last one, can you explain a bit more about windowing?
Sure, I'll try. So I guess in ksqlDB, they have this concept of windowing, which you don't necessarily have, I guess, in a normal SQL database. But the way it works is there's actually 3 types of windows that you can have. We only looked at a tumbling window in the demo, but so there's a tumbling window, which is a selection of time, and then that'll be like 3 seconds. Then we'll move on, another 3 seconds, another 3 seconds. So the individual windows, one after the other. But then there's a hopping window, which is basically it's the same, consecutive time windows, but with a hopping window, you could have the window restart every time a new event hits. So a hopping window would mean that you could have the same record in one or more results, if that makes sense. And then that's because as that record comes in, it might suddenly exist in 2 windows: the start of its own window and a window that it might have been the second event in. And then the third type of window is a session window, which we didn't really explore, but it has to do with activities. So if you have a cluster of events come through, then a window of inactivity or no events, and then another cluster that sort of identifies these as sessions where the events have come through. The windowing stuff can be quite complex and mind-bendy. So I definitely recommend checking out the Confluence docs for that, because they actually have some really Confluent have some really nice blog posts with some illustrations of windowing and how the events fall into each category. But the rule of thumb is if you want a unique event in a window of time, you don't want it to be duplicated, you can use a tumbling window, which is what we used for our example with the user views by add type.
I guess it's worth mentioning that this is sort of what makes what gives you like a type of an answer for what's happening instead of like in the old times. I mean, if you didn't have this option, you would have to do like batch process something and then get an answer later, right? But with this thing, you could get like an answer to your question while it is happening, right? So sorry, I didn't explain that fine, but yeah, I think those were all of the questions we had. Thank you for your time and have a great day.
Thanks.
Nå ser jeg at det har blitt mye enklere å selge bilen på Finn. Altså det hjelper med betaling og eierskift og...
Ja, men det blir sikkert enda enklere I fremtiden. Altså da blir det sikkert selvselgende biler eller noe. Ja, det vil jeg gjerne ha.
Bare sett deg inn I bilen, du, Kira.
Gratulerer, kjøper funnet.
Ja, der solgte den seg, ja.
Ja.
Bukken ikke veier snu, altså.
Kjøper funnet.
Ønsket du deg en ny bil, eller?
Ja.
Hei, gratulerer med ny bil.
Ja, nei, kanskje ikke.
Velkommen til vår smidigste bilhandel. Foreløpig I hvert fall.
FINN.no